to challenge problem number 4. Shooting Robert in.
Problem number 4. Accept.
So the reporter have 5 minutes to prepare. Please write down the name of the presenter on the record. Okay, so reporter, you have 12 minutes to report.
Okay, thank you. So, good morning, everyone. We are the team from Kansas International School, and we're going to talk about question number 4, shooting rubber band. So, here's our problem statements. A rubber band may fly a longer distance if it is non-uniformly stretched when shot, given its spin. Optimize the distance that rubber band with spin can reach. Explain and investigate this phenomenon. And we're focusing on 3 questions. How do the stretching and twisting of a rubber band affect its shooting distance? What impact do the physical properties of the rubber band have on its flight performance? And what role does spin play in the flight stability of the rubber band? And we're going to talk about three things: the phenomenon investigation, and experiment, and the data analysis. And at the end is the conclusion. So let's begin on our observation. So the measured composition of rubber bands affect their stretchability and durability. It means that the physical, the rubber bands, the new or its use affects its stretchability. And the humidity and temperature, it might affect the rubber band's elasticity and subsequently its performance. And the last one is the rubber bands with spin tend to have a more stable and longer flights compared to those shot without spin. So let's move on our possible variables. There are 3 possible variables. The first one is the degree of non-uniform stretching. So the difference in the force of stretching on either side of the rubber bands during preparation for launch. The second one is the launch angle. It means the angle between the rubber band's trajectory and the horizontal plane at the moment of release. This angle significantly affects the flight trajectory and final landing point of the rubber band. And the last one is the width and thickness of the rubber band. Wider or thicker rubber band may exhibit different flight behavior due to greater air resistance and different elasticity characteristics. So let's begin on our experiment. Our experiment equipment. We have the rubber band, bamboo stick, ruler, angle measuring instruments, and thermometer. So the rubber bands, every time we do the experiments, we use the new rubber bands to make sure that it won't affect our results. Also, we will have the different kind of the rubber bands, so it have the different thickness. Also, this bamboo stick, it is to use to hold the rubber bands during the shooting. And the thermometer is to fix the temperature within a certain range to make sure that the environment won't affect our results. Our experiment procedure. First, we're going to decide on variable that we want to test. So we have non-uniform stretching degree, launch angle, and rubber band dimensions. So the second thing is we mark path to measure the distance each rubber band travels. So after these, we'll repeat doing the experiments and we analyze it. So let's move on to our experiment 1. The operating variable is the non-uniform stretching degree, and the control variable is the type of rubber bands with it, which is the thin one. And the environments and the launch angle, which is 30 degrees. So as you can see here, the picture is here's the black points and here's the not black points. So we pointed out 2 points on the rubber band, so I can stretch it to have a different force. So it's our data, and 5 centimeters, 4.5, and 4 centimeters represents the distance between the 2 points that I pointed on the rubber bands. So the shorter distance between 2 points will result in further flight because it will force greater force on the rubber bands. And the reason of it is the conservation of elastic potential energy in kinetic energy. So the function here is the elastic potential energy. And the K is the spring constant, or we can represent it the equivalence constant for a rubber band. And the X is the distance that the elastic object is stretched or compressed from its equilibrium position. So, and this function is the kinetic energy. The m is the mass of the rubber band, and the v is the velocity that during the flight. And we put these two functions together so we can know the energy that change between. And here is our resource. So let's move on to our experiment 2. The operating variable is launch angle, and the control variable is the type of rubber band, which is the thin one, and the environments and the non-uniform stretch degree. So as you can see in the picture, I will put the bamboo stick with a different angle here, and this line is the horizontal line, so we can use the angle measuring instruments to know the angle. And here's our data. So I experiment 30 degree, 45 degree, and 75 degree. As you can see, during the 30 degree to the 45 degree, the distance increase. However, when I change the 45 degree to 75 degree, the distance decrease. So I get a result that the distance is proportional to the launch angle. However, if it is greater than volume, the distance will decrease. And I measured that the 45 degree is the best degree to form the maximum distance. And the reason of it is the principles of projectile motion. The optimal angle for the longest distance in the vacuum is 45 degrees. But we have to ignore the air resistance and the other external factors. Also, the distance projectile travels is determined by both its horizontal and vertical components of velocity. So at 45 degrees, these components are equal, so it makes the maximizing the range. So to figure out the distance, we assume the projectile's initial velocity is v0 and the launch angle is theta. So as you can see, it's the horizontal formula and the vertical initial velocity formula. And then we're gonna assume the accelerator due to gravity is g and the flight time is t. So for the vertical upward motion, the flight time t can be calculated through the vertical initial velocity and the accelerator due to gravity. So at the end, I'm going to calculate the range that the maximum distance, which is the range, can be calculated through the horizontal initial velocity and the flight time. And here's our resource. And let's move on our experiment 3. The operating variable is the thickness of the rubber band, and the control variable is the environment, the non-uniform stretching degree, and the launch angle. And the thick rubber band we use is the 10. So here's our data. So as you can see, the thin rubber band forms a greater distance. However, the thick one have a shorter distance. So I get the thin rubber bands fly further than the thick rubber bands. Why? So the reason of it is the aerodynamics. It is to calculate this function is to calculate the drag force encountered by an object moving through a fluid, which is the air. And this is the drag equation. So the D here is the force, and the rho is the density of fluid. The air is approximately of the 1.25, and the V is the speed, and C to D is the drag coefficient, and the A is the cross-sectional area. So in our conclusion, there are some variable affected in the experiment results, with the uniform stretching, the launch angle, launch degree, and the thickness of the rubber bands.
So opponent, you have 2 minutes to question.
Okay, so first, you said that the humidity and temperature will affect the elasticity of the rubber band, right?
Yes.
And also, do you think the width will affect the results? The width of the rubber band?
Yes, as I mentioned, it will affect the aerodynamics.
And you can please turn to page 7. Okay, so page 7. Okay, so the last point you said a fixed temperature within a certain range. So are you controlling a fixed value or controlling it in just only a range?
So we do the experiments in the classroom, and we will close the window and the door to turn on the air conditioner to control it at the range.
Okay, so thank you. And for your second experiment, the results, can you please give me that picture?
This one.
The data for experiment, second experiment. Yeah, so you said that the distance is proportional to the launch angle, is it correct? Is that what you mean, proportional?
There's two. During the 30 degree to 45 degree, the distance will increase. However, during the 55 degree to 75 degree, the distance will decrease.
Okay, so if it is greater than the critical value, it will decrease.
Yes.
Okay, thank you.
Alright, so the next opponent, you have 3 minutes to prepare. is the opponent. You have 40 minutes to discuss.
Okay, this is the opponent from Team MDPH track, and I'm going to focus on the question shooting rubber band. And this is a problem statement. This is a problem statement, and I don't think they have any clear main focus on it. And this is a summary of the reporter. So for the theory, they're going to focus on the elastic potential energy and the kinetic energy, and also the aerodynamics. And the setup of their experiment is rubber band and blue state ruler thermometer controls the temperature and the angle measuring instrument. And the parameters they're going to change is the degree of non-uniform stretching, the launch angle, and the width and thickness of the rubber band. And they're going to analyze the distance that the rubber band can fly. And these are the overall advantages and our suggestions to the reporter. So first, they have great coherence and organization explaining how they are going to investigate this phenomenon, and their explanation on the theory after their results. And we suggest that they need a clear expression about their theory and how they derive their equations, and the comparison between their experience data and theory. And yes, and these are going to be the points of discussion that I want to focus about mainly later in the stage. And first, I want to talk about how to quantify the effect of elasticity on this motion. And second, they stated that they have a critical value in experiment 1, and I want to know about know deeper about the critical value. And third, they didn't mention the consideration of rotation because the problem statement said that they need the rubber band to spin. So I think that it might have something to do with the rotation. And also, the drag force in projectile motion. I think that they need to consider the drag force for the formula in experiment 2. And at last, the relation between the distance and launch angle, which is also affected by the drag force. And this is the overall summary now. Okay, so first I want to ask you, you said that humidity and temperature will affect the elasticity. And do you have a formula or any methods to investigate how it affects the elasticity?
No, we assume that it might affect it. So we can be able to make sure that the environments won't affect our results.
Okay. And how do you think the elasticity will affect the experiment results? Like for different elasticities, according to your presentation, different elasticities might have different results, right?
Yes.
Then how do you think will change the results?
I think it will be stable, but I think there's might be a value that when the elastic is greater than that value, it might be unstable and decrease the distance of flight.
So you're saying that there's going to be a value of, like, sort of critical value of the elasticity that might affect the results.
Yes.
Okay, then why do you think that there's a critical value?
Because I think the elastic it spin, but if you spin too fast or too much, I think it won't increase its stability. So it might decrease the distance of flights.
Yeah, okay, so what I suggest is, because we can really predict the trend of different elasticities, so maybe you can conduct another experiment, like investigating how the elasticity will affect the results and what values will have greater distances for elasticity.
As I mentioned, we we have the different distance between the 2 points. So we do have the different force of the spin to force on the rubber band to make it spin.
Yeah, but I'm talking about the elasticity. Like you said, elasticity would. That's okay. So what I'm trying to say is maybe we can have another experiment to investigate how the elasticity will affect the result. Yeah, and that's okay. And the next question I want to ask is, the problem statement said that the rubber band will fly a longer distance when non-uniformly stretched, and then giving it a spin. So do you think that the rotation of the rubber band will affect the results? And did you take that into consideration?
Yes, in this experiment, it will force a different spin to the rubber band, so it does affect the distance.
Then how can you know that how is the effect of the rotation of the rubber band according to your, do you have any formulas or theories to prove that? Do you have any equations or formulas relating to the rotation to predict that how it will affect the results?
So you want to talk about the formula of the rotation?
Yeah, do you have any?
No, we don't have.
Yeah, so talking about spin, you have one page that you talk about the potential energy, that's the elastic potential energy and the kinetic energy, right? Yes, and because
This one?
the main factor, and because the main factor affecting this phenomenon is obviously the spinning and not spinning, right? Because for the spinning of the rubber band, you have longer distances.
Yes.
So I think that for this equation, we can consider adding the rotational kinetic energy, because do you agree that if something is rotating, it has a rotational kinetic energy, right?
Yes.
Yeah, so I think that the rotational, the energy for the rotational part can be considered inside. Do you agree with that?
This formula, I assume that the different force to spin for it will affect the distance. And so I only talk about the change of the energy of it. So I agree with your points.
Okay, then, so now if you want to add the rotational kinetic energy, can you sort of write on the blackboard how will it affect this formula? How can you do better on this formula instead of only elastic potential energy and kinetic energy?
Okay, so can you repeat it?
We said that we want to add the rotational kinetic energy inside, right? Inside this formula.
Yes.
Then, where are you going to add it? How can you transform this formula into a formula considering both kinetic energy and rotational kinetic energy?
I think we can add a rotation in this formula, because it is only this formula is only talking about the change of the elastic potential energy and the kinetic energy.
Yeah, but just now you agree with me that there's rotational.
Yes, so I think about it, so I'm going to change my answer, because this is only talk about the change between the elastic potential energy and the kinetic energy.
Okay, so now you think that we don't need to add rotational kinetic energy?
I think we can figure out that we can have another formula for the rotation for it.
Yeah, okay, so I think we can discuss about it working on that. Okay. So this formula, you're only talking about the elastic potential energy, and then it transfers into the kinetic energy, right?
Yes.
And this is the kinetic energy of the rubber band, the translational kinetic energy, right? Like the rubber band moving in the speed, it has a energy. Okay, so what I said is, do you think that this will change into only kinetic energy, translational kinetic energy, or other energies, such as the
you mean that
rotational kinetic energy?
you think that there's the energy that moves during the changing?
Okay, then let's ask it in another way. Do you think that this will change into rotational kinetic energy also?
Yes.
Yes, okay, so do you know how rotational kinetic energy is defined?
Rotation energy.
Yeah, how is it defined? Rotational kinetic energy.
Maybe you can introduce it.
Okay, so relating to kinetic energy, the rotational kinetic energy is have 1/2 times the rotational inertia. Do you know what that is? Okay, and times the angular velocity squared. Like it's something that would be like the translational kinetic energy. So I think all I think is you can add these two together because this will both transfer into the translational kinetic energy and rotational kinetic energy. Do you agree? Yeah, alright, so I think this is a better way of explaining your data. Yeah. And again, focusing on this equation, you said that that's it for energy. So when you shoot your rubber band, you have different like forces on either side, right?
Yes.
Then will the kinetic energy, potential, elastic potential energy be the same for two sides of the rubber band? What do you think about that?
Because there's only one side is stretched. So I think the potential, elastic potential energy only, it's only on one side, that which is the side of it's stretched.
So you're saying that the other side is not stretched?
Yes, because I only stretched the 2 points that, and I will stretch it until the rubber band, the 2 point is on the other side.
Okay, so like, just as you said in your experiment, let's say this is a rubber band, and then you take like 2 points,
Yes.
and then you stretch these 2 points, right?
It's
Like this part, but this part. Then why isn't this part stretched?
because I didn't stretch it. I will hold these 2 points and stretch it until the 2 point is on the other side. Do you know what I mean?
So this part is loose, it's not tight,
It is not stretched.
it's not stretched. Okay. Then how do you explain the like how this part affects the results in this experiment?
So we have the different distance between the 2 points of it. So we have the different stretch, and also we can form different split.
Okay, time's up. So the opponent please summarize the discussion. You have 1 minute.
Okay, this is a summary of the point of discussion that we discussed. And so first, I asked about the effect of elasticity in this experiment because they said it will affect. And we suggest that they can conduct another experiment because they said that they think there will be a critical value for the elasticity affecting. So we think that they should conduct another experiment doing different elasticities. And mainly in our discussion, we mainly talk about the rotation of the rubber band because this is what the problem statement wanted us to investigate. And we agreed that we should add the rotational kinetic energy into consideration. And we think that the elasticity potential energy will not be the same on the both sides of the rubber band.
Time's up. So next, the reviewer, you have 3 minutes to question reporter and opponent.
So, first for the reporter, did you control the mass and pay of rubber band when changing
Yes, we buy the same rubber band.
But how, wait, I mean, the thickness is different, so they're different from.
There's two kinds of rubber band. One is the thin one, one is
But
the.
did you control the mass and pay?
Yes, it has the different mass of the thick one and the thin.
Then how did you launch? Like, make the rubber band?
So you want to.
Oh, I want to check the return
Of the launch angle?
You do have photo of that.
No, I don't have the photo.
I give the numbers in this. Okay, so for the opponent, do you think that half kx squared is correct? So, like, I mean, like in this condition, do you think that you can describe the energy of the rubber band as half kx squared?
Well, in some limitations, it can be used as in the Hooke's law, and then we can use the potential energy as half kx squared.
Okay, so for the reporter, do you so you use this equation because you believe it is suitable for the Hooke's law?
Yes.
Yeah, but did you do the experiments like the relationship between f and x? Or did you just assume that Hooke's law can be applied in this situation?
Can you repeat your question?
Did you first make a different experiment to check that f is so the relationship between f and x is the same as the condition in the Hooke's law?
No. I assume that.
Okay. So for the reporter, do you think that, for the opponent, do you think that the reporter should make sure that f is proportional to x first, or do you believe
Yeah, of
that?
course, because it is only limited to the forces under the elastic fatigue.
Okay, time's up. So next, the reviewer, you have 2 minutes to prepare. Okay, time's up. So reviewer, you have 4 minutes.
Hello, I'm the reviewer of requested shooting rubber band. This is the problem statement. So first, this is the summarize of the reporter. So the reporter lists focuses for the problem to discuss, and they simple mention about the theory. They mention that when the rubber band is non-uniformly stretched, and also in conditions like 45 degrees, and also the rubber band is thin, then the result, and for the result, the rubber band will travel farther. And then they have 3 parameters, including launch angle, width, and stress. And they mention about the material, humidity, and also the temperature might affect. For the reporter, there are some strengths, including that they managed to control the temperature in a certain range. They clearly stated what to discuss, and they listed the procedure for their experiment. And for the areas of improvement, they have lack of pictures to show their improvements. They did not show the lecture set up for discussion for possible errors. They don't have a graph, they only have a table. They mentioned about the energy formulas, but they did not apply some other things like rotation and air resistance. They did not make sure the rubber band can apply to F equals Kx, and they did not consider other energy losses. And for the opponent, their strengths are, so they clearly describe, so they have clear physics description, and they organized the reporters lack of theory like for the rotation, and they pointed out the energy did not only transfer to kinetic energy, but also like rotation. And for the errors of the improvement, they did not ask the reporter about the experimental setup, and they have some lack of consideration like air resistance. And so first, this is the discussion. First, the opponent asks how the elasticity affects the distance and why. For the reporter's response, he said that over a certain value might decrease the stability, and spinning too fast might make the rubber band unstable. For this point, we agree with the opponent that they should do some more further experiments to explain this. And then the next one, the opponent talked about their rotation. And for the reporter, they showed their data, but they have lack of theory. At this part, we agree with the opponent that they should also consider the theory of rotation. The next one. The opponent said they should add rotational energy to the formula. For the reporter, they agreed, but for the reviewer, we think that air resistance should also be considered. And, so they should for the reporter, they should make sure that K and M is the same when they change the thickness of the rubber, which they do not do. And also, they did not mention that they measured K and V and.
Okay, time's up. So next, reporter, you have 2 minutes to conclude.
Raised the point that we need one more formula that is talking about the rotation energy, and we agree with that. And we explained the theories clearly and their connections to the experiments. We had a variety of good control variables in order to find the best results. Hence, the error is not as important. rubber band's air resistance is very small, and it's especially hard to measure when the rubber band is spinning.
Okay. So, any questions from Rory?
So, during the discussion, we all know that the rubber band can be stretched, and as the reporter mentioned, that the mark 2 points to make the stretch length of the two sides different, and could transform into both translational energy and rotational energy. So I have one simple question for you all. If we control the mark points and the stretch length such that the initial velocity of the rubber band is the same, but the angular speed is different. For example, high, middle, and low. So how do you think the distance, the final distance of the rubber band? How do you think? Okay, how about you?
For different angular velocities.
Yeah, but the same initial velocity for translational.
I think that the angular velocity has something to do with the aerodynamic effects, and
So
it will.
the result.
Oh, the result is that bigger angular velocities will have bigger distances.
So if it doesn't rotate, then the distance will be shorter.
Yes.
Okay, how about you? So the reviewer and reporter?
Can you repeat your question?
I mean, the same initial velocity v with different rotational angular velocity. How do you think the final distance if we have larger omega?
Distance will increase. We will have a longer, further distance.
Okay, I see.
Okay, so reviewer, you want to answer the question?
Okay, so when the angular velocity is bigger, the spin becomes more stable. And also resistance might decrease the air resistance. So I think it can by itself.
Okay. So, any questions from Rory? If no, let's prepare this. Alright, so the score for the recorder, 47535. And the score for the opponents, 58877. And the score for the reviewer, 66876. All right, so thanks everyone. We have 10 minutes break. Please be back.